So today is the third of the series of lectures on CUDA. And so let me recap what we saw last week. I gave you a few ideas on how to find mistakes and errors in the CUDA code, because you need to be a bit more careful because you're running thousands or even millions of threads simultaneously, and finding mistakes can this requires delicate tools. The other thing we saw is a recap of all the functions to manage allocate, copy memory, initialize memory, and so on. And then I discussed CUDA kernel. So this is really the heart of what's specific to CUDA, because these are the special kind of functions that allow you to perform in parallel the same computation on all the entries of an array, for instance. And one thing I mentioned towards the end is that CUDA kernel, the threads in a CUDA kernel are organized in blocks of 32 threads. So this is the smallest group of threads that will be run in parallel. And the hardware is such that there is a big benefit to having these 32 threads performing exactly the same task at the same time. It's allowed to have branches even among these groups of 32 threads, but it implies that if you have really several branches, then the 32 threads will diverge, which means essentially that they will perform one branch and then the next branch, but this will not happen simultaneously. So of course it has an impact on the performance. So today I want to discuss three topics. The first one is about synchronization and what is called streams. So this is a set of functions that allow you to have certain tasks work in a synchronous way, while other tasks can work independently of this first group. So for this, you need the concept of streams. And then second topic today will be shared memory. So how it's used, what is it, what's the purpose of using shared memory, and what's the syntax for using it. And then I will illustrate this by one example of calculation, which is very frequently performed. It's called a reduction. So reduction typically is you start from a large array and you want to produce a single number out of this array. So for instance, an array of numbers, and you want to compute the sum of all the elements of the array. And you want to make that as parallel as possible. So of course, this is something that will also be doable on the host computer. We will see the difference in performance. There is one, but it's not huge. But sometimes it's data you've produced on the GPU, and it's preferable to do the reduction also on the GPU to save the cost of transferring this array back to the host. So we will learn how to do that on the GPU in parallel. And then these are the topics for next week. So let me start with streams and synchronization. So I think I mentioned that already last week. When by default, when you have CUDA instructions code, they are put in a kind, they are queued in a sort of pipeline, and they are executed in order. So if you put a memory operation to copy some, and then you have functions that will operate on data, they remain strictly ordered, so the function will only start after the memory copy is finished. And this makes sense because when you have a single queue like that, want the data to be copied before you start doing computations on this data. So this makes perfect. There is a name for this in the CUDA jargon for this kind of pipeline. It's called stream. So it's here. This is a stream, so it's like a flow of successive instructions. And by default, each GPU has a single stream. It's called the default stream. And it has an identifier which is just a number 0. And if you don't do anything special, all the tasks you submit to the GPU, they will be queued in the default stream. Now, if you have a computer with more than one GPU, each GPU has its own default stream, so it means that there is no synchronization between the tasks you submit to the first GPU and the tasks you submit to the second GPU. So if you need this kind of synchronization, you better be careful. But also something I want to mention is that, so by default, each GPU has just a single default stream, but there is an alternative which is obtained by giving a special option to the compiler, which is to have one default stream per GPU, but also per thread on the host. So for instance, if you create 4 threads on the host by using OpenMP, for instance, there are certain problems where it's a good thing to have one CUDA queue or one CUDA stream for each of these threads on the host. So the thread number 1 has its own queue of events, and the thread number 2 has its separate queue of events. So the option to do that is you just put this compiler flag, which is minus default stream equal per thread. And when it compiles, it will create one stream or one queue of this one pipeline for each thread. And now, if within using OpenMP, you can submit tasks to different CUDA streams. So this is something I already mentioned, that if you have 2 GPUs, the sequence of CUDA events on the 2 GPUs are not synchronized at all. So if a task on GPU 1 depends on the completion of another task on GPU 0, you need to do something. So for instance, if GPU 0 is computing something and then is responsible for transferring the result to GPU 1, and then GPU 1 does another computation on that, you need a way to tell GPU 1 that it's okay to start doing the computation because the data has been transferred. By default, this will not happen, and of course, there is a risk of trying to use this data while it has not been copied yet. So for doing this, there is the notion of CUDA events. So it's a tool that can be used to ask the host thread to wait for certain tasks on the GPU to be complete. So the typical usage is that you have to define a variable of type CUDA event. And so this is just an empty handle when you do this. And then you have to call this function CUDA event create that will initialize this event. So an event is not just a number, it's a structure that contains various informations about CUDA tasks still in the queue. And then the way it's used is that suppose you have a sequence of CUDA commands, let's call that A to simplify. And then you have another set of CUDA tasks, B, that should only start after A has been finished. Then what you do is that you issue all the commands of the sequence A. You call this command CUDA event record with this event created and mentioning the stream we want to record. And what this command will do is that it will store in this event variable all the unfinished tasks that there are still in the queue at the moment you call it. And then the way to wait for all these tasks that have been recorded in the event is to call the command CUDA event synchronize, and this command will block the execution of the host thread until all the tasks that were recorded in the event have been finished. And then the tasks listed in B will start only after those that were recorded from A are finished. So this is convenient, yes.
So if I understand the task, if there are new tasks in the 3-dot lines, the line those are not.
Those are not in the record, and the synchronize will not wait for them.
Okay.
So here in these dots you could have another set of tasks that B doesn't care about because B could start even if those are not finished.
Okay.
This is so the record will just register all the tasks that have been submitted until the time where the function CUDA event record is called. Just a trivial remark. If the tasks of A and B are in the same stream, of course, you don't need all this machinery for synchronization because everything which is in the same stream is by default synchronized. So this is useful when you want to synchronize tasks that are in different streams, for instance, because they are on different GPUs. You can also use these CUDA events if you want to assess the performance of your code. So you want to time the duration taken by a certain CUDA commands. So for this, you create two events, an event you call start and another one you call stop. And you initialize them. You first call CUDA event record for initializing the start event. Then you do some stuff. The some stuff is the set of commands you want to measure the time. And then you do another CUDA event record, but now with the stop event after you've issued all these commands. And then you call CUDA event synchronize to block until all these tasks have been finished. One thing I didn't mention is that this variable of type CUDA event, one of the fields in it is a timestamp, and the timestamp is updated by CUDA event synchronize. So the timestamp, when CUDA event synchronize returns, the timestamp inside these variables will be set to the time when the task have finished. So this way, you have the information about the time it took, because then you have this function CUDA event elapsed time. So you give it the two events, start and stop, and it will calculate the duration between the two. Yes?
Could you have several streams on the same GPU that would make use of CUDA events on
yes.
one GPU?
Yeah, so CUDA events can be used also for synchronization between different streams on the same GPU. So I will explain next how to define or how to initialize and use more than one stream on the same GPU. Yes, of course, because if you create several streams on the same GPU, they are also not synchronized by you.
Can you reuse the events you created?
Yes, so you create it once, and every time you call CUDA event record, for instance, it's updated by the new tasks that are in the queue at this moment. You don't need to create a new one every time you want to call one of these functions. And in this function, CUDA event elapsed time, duration is a pointer, or duration is a float, and what you pass the pointer to the address of this float to the function, and the function will write in it the duration in milliseconds. And I've read somewhere that the resolution of this time measurement is half a millisecond. And there are cases where you don't really care about the precise time in milliseconds. What you care about, well, because that's a better measure of how your code performs, is the bandwidth. This is the case for any computation which is limited by the time it takes to read the data in the memory. So for instance, I will show you an example next week, which is sort of calculating the transpose of a large matrix. The transpose is a trivial operation. You have two elements and you flip them. So the computational aspect of the transpose is trivial, it's peanuts. And what sets the time it takes is how fast you can read the elements of the matrix in the memory. So for this, to assess whether your code reaches peak performance or is far from it, you should compute the bandwidth at which it operates. And so if you have the duration of certain operation, CUDA operation in milliseconds, you have to count how many bytes are read and written by this function. You divide the total amount of data transferred by the duration, you multiply by 10 to the minus 6, and you have gigabytes per second. Okay. So this is the way to estimate the performance of code, whose performance is limited essentially by the memory. So now let me come to this topic of creating your own streams. So far we saw how to use how to use a default stream or have several default streams, one per each thread of the host. But there are cases where you don't even have more than one thread on the host, but you still want to have more than one stream. So it's possible to create additional streams. So there is a type which is CUDA stream, and it's the same. You have this will just create string variable, but it's initially empty. And then you call CUDA stream create with the address of the variable, and it will initialize it. These streams that you create by calling these functions, they can be used in all the async version of the memory manipulations, for instance, to tell that this particular operation takes place in this particular stream. Just one remark, because I've learned that the hard way, and it's something to keep in mind. A stream variable is not big, it's not large, it's a few bytes, I guess. But if you create zillions of them in a loop and you forget to freeze these variables, eventually you will run out of memory. So usually streams are something you create a few of them at the beginning of the execution of your program, and you do all the rest of the rest of the program doesn't need to create more streams. If you create them in a loop, even though they are only a few bytes each, eventually. So I didn't say it, but there is a function which I think it's CUDA stream free, perhaps. If you ever want to destroy a stream variable, you have to call it. So what are the properties of the created streams? So first of all, when you use only the default stream, multiple kernels cannot overlap, even if the resources necessary for them would exist. So for instance, if you have a kernel that has only 1,000 threads and another kernel that has also only 1,000 threads, and you have a GPU with 10,000 cores, they will nevertheless not run simultaneously. when they are in the default stream. Also, kernels, so the functions that compute, and the memory operations cannot happen simultaneously when they are both in the default stream. That's by design. Now, when they are issued in different streams, two kernels can be executed simultaneously if the GPU has enough cores to satisfy both of them. And in situations where there are not enough cores to run two kernels simultaneously, you can still have one kernel from one stream happening at the same time as the memory transfer in another stream. But the only thing you have to be careful, obviously, is that the memory transfer in the other stream should not use data that is written or read by the kernel doing computations. Otherwise, presumably, the outcome will be undefined. So this is used in this way usually, either to do two computations at the same time, or to do at the same time some memory transfer and some computation. Of course, there is no miracle in the sense that if your GPU has 10,000 cores and you have one kernel with 1 million threads and another kernel with 1 million threads, probably they will not run at the same time, even if you put them in different streams. But they could, if, for instance, one of these kernels has to wait to access some data in memory, then the other one can run and do computations. So there are certain rules for how they are synchronized synchronized among themselves or with the default stream, because when you create streams by hand, you still have the default stream still exists. So the rule is simple regarding the default stream. The default stream synchronizes with everything. So if you have this sequence, for instance, where you have a first kernel which is sent to a stream with a stream handle S, and then you have a second kernel which is sent. There is no further arguments here, so it means it's sent to the default stream. And then the third kernel, which is again sent to the stream S, then they will be happening in sequence. So kernel 1 will finish first, and kernel 2 starts only after kernel 1 has completed, and kernel 3 starts only after kernel 2. This is because the default stream has precedence over everything else, and everything has to wait until because of the things in the default stream. Now, if you create one default stream per thread, so per host thread, then the behavior is pretty much like the streams you create also by hand. They do not synchronize among themselves. So if you create, if you have two default streams, one per thread, they are not synchronized. And the user-created streams do not synchronize with one another, which is their main benefit in a sense. That's why you usually create streams in the first place, because they are not synchronized, and you do that because you know there are certain tasks which do not need synchronization. So the logic for creating streams is that you have to analyze which tasks depend on one another or do not depend on one another in your code, and you put in the same stream the tasks that depend on one another, and you put in another stream tasks which do not depend on the first set of tasks. So now let me turn to a slightly different topics. There are situations where one would like to, or some level of synchronization among the threads within one kernel. So suppose you have within one CUDA kernel a certain operation that must be completed by all threads before you continue. So there is a way, at least at some level, to do that. You will see it's not possible to do that for all the threads, but at least for all the threads that belong to the same block, it's possible to have this kind of synchronization. So first of all, if we start at the level of what is called the warp, so these groups of 32 threads, usually there is no need for a synchronization among those because by design of how the GPU operates, they are always synchronized. They do the same thing at all times. So the next level is that of a block, size of which you define when you call the kernel. So there is this function with 2 underscores sync threads, and there is no argument between the parentheses. So this function, you place it in the CUDA kernel, and it will halt the execution until all threads in the block have reached this point. So you can use the typical usage of this function is that you have threads that write in shared memory, and then later on the data that has been written in shared memory will be read, but it might be read by different threads than those who wrote the data. So if you don't want to have this problem of some threads trying to read this data before it has been written, you have to place this function sync threads between the writes and the reads to this data to order them. So it's also called the memory fence in the CUDA jargon. One very important thing to remember: sync threads really blocks until all the threads in the block have seen it, have reached it. So if you put this function sync threads within a conditional branch, and not all the threads in the block take the same branch, there is a risk that some of the threads in the block will never execute this function, and therefore your program will block indefinitely. So if you have conditional code with the sync threads inside, you have to make sure that the condition will evaluate to true for all the threads in the block. Otherwise, the program will not work. There are several variants of this function. So the basic one is the one I described, sync threads. So it halts until all the threads in the block have reached it. There are 3 more, at least there are probably a few more, which perform additional things. So sync threads count takes an argument which is a condition, so like a test of some variable is positive, for instance, and it has the same property of blocking the program until all threads in the block have reached it. And in addition, it returns an integer, which is the number of threads in the block for which the condition was true. So it's, for instance, if you want to test, you have an array, and you want to know how many numbers in this array were positive and how many were negative. You could use this function to do this test just one instruction. There is another variant which is sync threads and, so it is the same. It takes an argument which is a condition, and it returns true if all threads, if the condition was true for all threads. So this, for instance, if you want to test that all numbers in the array are positive. And then there is a variant which is OR, so it returns true if the condition is true for at least one thread in the block. So this is sometimes useful rather than coding that by hand yourself. There are several functions that do some form of synchronization at the level of a warp. So these smaller groups of threads that have 32 threads in them. So the function is called sync warp. And the syntax is that it takes also an unsigned integer. So you can view that as 32 bits. And the binary representation of this integer tells to the function the threads that should be taken into account. So you can exclude certain threads from this behavior of blocking until they have all reached this. So if you want to say all threads matter, then you put the 32 bits to 1. That means in hexadecimal it's FFFFF. I've never used this function because I've never had a situation where I wanted this fine-grained level of synchronization. And then there are other functions which can do pretty much the same as these functions here, but for the smaller groups of 32 threads. So the first one is testing whether a certain condition is true for all the threads in the warp. And again, there is this variable, this mask, which specifies which threads you take into account when you do this. You don't have to use all 32 threads. There is one which is any sync, so it checks whether the condition is true in at least one thread. And then there is one which is called valid sync, which counts the number. No, it doesn't count. It returns an integer whose bits are 1 if the corresponding thread had the condition true. So this is for doing more fine-grained tests of what happens in this thread. So now I'm coming to the more important part, which is the way synchronization works is by using a shared memory between the threads, but shared memory, or at least only the threads that belong to the same block do see the same shared memory. So there is no way this mechanism will work for synchronizing threads that do not belong to the same block. And in general, there is just no easy way to do that. So one uses synchronization at the level of the blocks, and if you ever need synchronization for all the threads in the kernel, it's better to just divide your kernel in two, the part before where they need to be synchronized and the part which is after the threads need to be synchronized, because when a kernel terminates, it's a point where all threads, by definition, are synchronized. They have all terminated what was. So, and another reason why it's problematic to synchronize threads that are not in the same block is that they may not run on the same chip inside the GPU, but they may not even run at the same time. The GPU or CUDA does not promise you that if you have a kernel with 1 billion threads, they will all run at the same time. In fact, it's physically impossible. So they run by batches which are successive. Okay, so this is all about synchronization. With all the functions I've described here, you can satisfy most of the needs, but it's far from being exhaustive. Yes.
Because what you want, you can optimize that in a given block.
No, but it's not true that you can have any number of threads you want in a block. There is a maximum, which is 1024. It's true that they will perhaps not run all at the same time, but what is guaranteed is that they will run on the same chip and use the same shared memory. I don't know how the hardware deals with that, but if it has to separate the threads of a block in successive batches, it will still keep some internal state so that they can communicate even if they don't run at the same time. But not across blocks, only within one. Okay, so now I want to move on to the topic of shared memory. So this is a picture I showed, but I've added just one more decoration. What I've added compared to what you saw 2 weeks ago is this green rectangles, which represent the shared memory. So the shared memory is a part of the L1 level 1 cache, and it's something which is configurable. So you can decide you don't need it, or you can decide you want a certain amount of shared memory. And the consequence of being in the L1 cache is that, first of all, it's seen by all the cores that belong to the same chip, the same stream multiprocessor. And because it's part of the level of cache which is the closest to the computing cores, it's also very fast memory. So it's memory that takes only a few clock cycles to read or write to. And so there are two main usages of shared memory. The first one that we will see when we discuss reduction operations is that it's used as a way of exchanging data between threads that belong to the same block, so as a way of communicating between threads. And sometimes it can be used as a way to reorder the sequence of memory operations to put it in an order which is more favorable to the bandwidth. So we will see an example where it's used in this way next week. It's the example of calculating the transpose of a large matrix. So maybe I can just explain a little bit what the problem is. So CUDA likes when all threads read memory in the sequence of the thread index without big jumps in memory. So when you read the matrix, so first of all, you choose a layout for the matrix. The matrix is two-dimensional, but in the memory of the GPU, it's just one large one-dimensional array. So you have to decide whether you use what is called row major, so you put rows in sequence this big array, or column major. You choose whatever you like. The problem is the same. So the problem of the transpose is that on one side of the equation, you're reading the memory according to following the rows, and on the other side, you're following the columns. So no matter which layout of the matrix you choose in memory, one side of the equation will have big jumps when you read or write, and this is not good because the bandwidth for when you do big jumps is very, very much deteriorated. So shared memory can be used as some intermediate buffer where you put your data, and then from shared memory you read it in the order that the GPU likes to maximize the bandwidth. So you will see how that works. So how to declare a shared memory? So first of all, a shared memory is not something you declare once for all at the beginning of the program. It's something which is defined kernel by kernel. So you can choose that one kernel doesn't need shared memory and another kernel will use shared memory. And then what you need to specify is how many bytes of shared memory per block you're going to use. So there are two ways to declare it. The first one is inside the definition of the kernel. So you put this, it's like variable declaration, and it's preceded by this keyword shared between underscores. So this tells that this kernel is going to use n floats of shared memory per block. So this is called static declaration of shared memory. I think the number of the size of the array has to be known when you compile the code. It cannot be something dynamical that will arrive through the arguments of the kernel, for instance. So this is the static declaration. That's what you use if you know at the time of computation how much shared memory you need. And then there is a dynamical way to declare the shared memory. So inside the kernel, you have to declare this array of floats, but you don't specify its size. You see that between the brackets, there is nothing here. You have to use a keyword shared as well. But now you declare it as extern, which means from the point of view of this function, it means you can use this array A and it's defined somewhere else. You don't have to worry about it. And somewhere else is, in fact, when you call the kernel, so this is the kernel call. So now you have to specify this third variable. And this third variable is the size of the shared memory you're going to request per block for this kernel. So here I put n times size of float, which effectively achieves the same thing as a static declaration. So this is used when the amount of shared memory is more dynamical, so it may vary from run to run or between different cores of this kernel. So here n doesn't have to be a constant, it could be another variable in your program. So how is it? So just one more thing. No matter which way you choose for declaring the shared memory, the way you use it afterwards is exactly the same, and there is no consequence of choosing one way or the other. Another thing which is important, this shared memory has a lifetime, which is until the current block of threads finishes. So you cannot hope to put something in shared memory that will be read later by another block, because this will not work. So it's only its duration is only while the block is still running. Okay, so one important thing is if you ask, so first of all, there is not so much shared memory you can ask. We're talking about kilobytes per block of threads. It's not, not megabytes, not gigabytes, of course, not even megabytes. It's more like few tenths of kilobytes. I will give you the figure later. I think the limit is 48 kilobytes. So it's to store little amounts of data. And a common mistake is to ask too much. So if you ask more than this limit, then the kernel will not run. Something will crash when it starts. If you are still within this limit, but you ask close to the upper limit, it means that only one block of threads can run at a given time. The GPU will not be able to run more than one block of threads because it won't have enough shared memory for having two blocks simultaneously. So it's always good to just ask the amount of shared memory which is absolutely necessary for your program, but not more than that. Otherwise, you limit artificially how many blocks of threads. So this memory, which is holding the shared memory, is on the same chip as the computing core. It's part of the L1 cache. It's super fast, and it's used for this reason to fasten certain algorithms. The size limit is 48 kilobytes per, it's not even per block, it's per stream multiprocessor for each of these chips. So if you want to have the possibility of having two blocks running at the same time on the same chip, you should not go over 24 kilobytes of shared memory per block. So this memory is seen coherently by all the threads that belong to the same block. So this is a very important property. And another thing is that if you have threads writing to shared memory, there is no guarantee that they will all write exactly at the same time. There could be a slight delay in some of the threads. And if your algorithm is later reading from shared memory, therefore, there is no guarantee that you will read from memory that has already been written, unless you put a fence between the reads and the writes. So this is a typical use of this function sync threads already described. You put the writes before, you have a sync threads that will block until all threads in the block are clear. And then you have the reads, and by doing this, you guaranteed that the writes have been finished before you start reading from shared memory. Of course, if a certain address in shared memory is written and read by the same thread in sequence, there is no need for that. But if that is the case, there is also no need for shared memory because the same thread can communicate with itself without shared. So another important property of shared memory that I want to describe, and this has to do with how it performs, or how to maximize its performance more exactly. And for this, you need the following information: that shared memory on a given stream multiprocessor is organized in what they call banks, and there are 32 of them. So you could imagine 32 little buckets holding part of the shared memory each. And the hardware is such that in a given memory operation, each of these 32 banks can provide 4 values. So in a single memory operation, you can get the value of 1 float for each of the 32 threads in the world. This is what we so that's a way to parallelize the memory reads or writes to shared memory. And when you store an array in shared memory, it's arranged with the following layout. So this array, I call it A, its indices are A0 and then go to A91. And then you see A0 is in the bank 0, A1 is in the bank 1, and so on. And then when you go back, when you reach A32, it's again in the bank 0, and so on. So this layout of the array in shared memory, you don't have to do that by hand, it's done by the hardware. It's done like this, but it's not something you can control. But the consequence of this arrangement of the array in shared memory is that if you have 32 threads that read 32 successive entries on this array, by design, these 32 reads will be in 32 distinct banks. So that the 32 reads can be done in a single memory operation. So all the 32 threads get back the value they need in one clock cycle. This also works for non-consecutive entries of the array as long as they will come from 32 distinct banks. So for instance, if thread 0 reads A0 and thread 1 reads A33, this is not a problem for performance. It comes from different banks, so it will, the two requests will be fulfilled simultaneously. What is not working well, at least works but with a penalty, is when the 32 threads access data that belong to the same bank, because then they will just be treated sequentially and there will not be any parallelization. So this is problematic, for instance, if you have, suppose you have a 32 by 32 matrix, and you flatten it in a single array, of course, as usual, and then you store this array in shared memory. If you're reading the rows of the matrix, everything is fine because you're reading sequential banks in the shared memory. But if you happen to read along a column of this matrix, you will access 32 numbers from a single bank, and therefore it will be much slower. So there is a trick that we will see next week to avoid this problem. It's a little cheat. You just declare it as a 32 times 33 matrix, and then they will be they will also be in different banks if you try to read the column. So when the read or writes to shared memory are not in different banks, this has a name. It's called the bank conflict. And essentially, when you have bank conflict, the hardware cannot provide the two numbers at the same time, or more than two, and they will be serialized. There is just one exception. It's when, suppose you have the 32 threads in the warp accessing A, all of them access A of 0, so the same address in the same bank, then this is treated as a single read operation. It doesn't need to read 32 times the same value A of 0. But this is not a common case. So yeah, this is something I said. So reading A0, A1, A2, A3 very fast, but reading A0, A32, A64, so all the multiples of 32 will be much slower. And sometimes you need to read both along the columns and the rows, and there is a trick to make it fast for both. Okay, so perhaps we stop here for the break, and then I will continue.
Yes, maybe we ask if there are some questions. Urgent questions.
So welcome back. So I stopped after having discussed the shared memory. So far it's a kind of perhaps abstract concept. So we will see right now an example where it's used. In this example, it's used more not as a way of optimizing the performance, but as a way of allowing communications and the exchange of data between threads. And then next week, we will see another example where it's really used to make the program faster. So now I want to discuss reduction operations. It's a very common task in computing where you have a large array of something, let's say n elements in the array. So a typical example of a reduction is that you want to this array is made of numbers, for instance, floating point numbers, and you want to compute the sum of all its elements. So the name reduction is that you start from an array, many numbers, and reduce that to a single number. Of course, the sum can be replaced by other types of arithmetic operations, or you could also have a logical operator. So for instance, the AIs could be the result of a text which is done that depends on the index I, and you want to calculate the logical end of all these tests to check whether the condition was true for all I. The only restriction on the kind of operations you do is that it has to be associative. So what this means is that, for instance, for the addition, it means that A0 plus A1 plus A2, if you put parentheses here, it's the same result as doing this. And the reason for this limitation is that depending on which algorithm you use to calculate the reduction, it corresponds to putting parentheses in a different way, which means starting by the addition on the left or right or the whatever. But if it's not associative, of course, the outcome depends on where you put the parentheses. And if you want a deterministic outcome, the algorithm should not change the parentheses. So the naive implementation of a reduction is not parallel. You start on one end of the array, for instance, at A to the A0, and you add A1, you add A2, and it's essentially sequential. And there are n-1 addition. So now let me explain what is the main problem with the parallelization of this kind of operation. So you have a certain array which is AI, and of course you want to calculate the sum of n elements of this array. This is the definition. So the algorithm is that you initialize S at 0, and then you do for I, you do S equal S plus AI. This is a typical algorithm for calculating the sum. Start from 0 and you add all AIs in sequence. So now, if you parallelize this loop, this is an obvious target for parallelization of this operation. The risk is that you see you update this S in every iteration, and the risk is that you have two threads. So each thread is doing this operation. It reads the current value of the sum, so the values of this variable S has reached at this point. It adds, so what by read it means it go and fetches it from memory and copies it to one of the registers of the processor. Okay. And then to this value, which now sits in the register of the processor, it adds AI and puts the result also in a register of the processor. And then the third step is that you copy this register of the processor back to the main memory. So it's really a sequence of 3 steps. And now, suppose you have 2 threads, thread 1 and thread 2, which both try to participate to the calculation of this sum. So the thread 1 pulls the current value of the sum from main memory, copies it locally, adds AI1, and then will write the updated sum back to the main memory. And the thread 2 wants to do the same thing, but let's assume that they slightly overlap in time. So the horizontal axis in this picture is time. And the thread 2 reads also the sum from main memory, but before the thread 1 has updated it. So then you see easily what happens. The thread 2 reads, in fact, the same values that was read by thread 1, and the thread 2 will add AI2 to the sum and write it back to main memory. And in fact, the update made by the thread 1 will be totally lost. Okay. So the main problem is this: when you have these concurrent updates but done by many threads. So it's already a problem with 2 threads, and it's a bigger problem if you have 1 million threads. So there is no miracle. And so to avoid this problem, there is a special instruction or kind of way of protecting this block of 3 instructions. Rather, it's called an atomic instruction, so that this combination, this sequence read, add, write is treated as something that cannot be cut in half. So it's called atomic. So there is that gives, and this kind of function exists also in CUDA. It's called atomic add here. So atomic add is adding AID to the sum in a way which cannot interfere with other threads. So it's putting the little flags before and after, and only one thread at a time can use this function. So this is a naive way of coding the reduction in CUDA. It's very naive because it's super slow, as you will see with the numbers below. So you just have, if your array has 1 million entries, you call this kernel with 1 million threads, and each thread will add its own little value to the sum, but in a way which cannot interfere with the others. So I tested that algorithm on my laptop. I took a large array with 512 million elements. I repeated the reduction 256 times so that the measurement of the time is less or more precise. And I had two versions of it. One version where the reduction is done entirely on the host using OpenMP with 6 threads. And then this naive reduction done on the GPU. And you see, in fact, if you use this naive algorithm on the GPU, it performs 6 times, 6 to 7 times slower than on the host. And I didn't include in the timing the time it takes to copy the array to the GPU because it was small anyhow. So this naive implementation is just too slow. And the reason why it's slow is that this atomic add that you use here amounts to saying the GPU, you compute this sum sequentially. That's why it's slow. So now
the result is not the same.
The result is not the same because presumably the host and the GPU do not have exactly the same rounding errors at each addition. And so this difference is the cumulated rounding error after 512 million additions. It's not too surprising that you get this difference at the end. It's not, I think it's unavoidable. I'm not overly shocked by this. It's done in single precision. You do really many additions. Each of them has a little uncertainty. There is no guarantee that two different hardwares will round additions or any operation, in fact, in exactly the same way. They make you a promise about the accuracy for each addition, but they don't guarantee whether it's rounding up, rounding down, or rounding some of the kind. So now let's look a little bit at this operation of summing the numbers of an array. And to simplify the reasoning, I will assume that the number of entries is the power of 2. So you have, let me make a picture with 8 numbers. So it's 0, 1, 2, 3, 4, 5, 6, and 7. So I have 8 values. So now, suppose I have hardware that can do in parallel many additions. So the way I would parallelize this is that I would compute the sum of these two, and if I have a parallel machine, these 4 additions can be done in a single clock cycle. Okay. So then I have 4 numbers, and then I repeat. So it's a kind of recursive algorithm. Now I have only 2 numbers, and then I do one more addition, and I get the final sum. Okay. So you see that starting from 2 to the power 3 numbers, this algorithm takes 3 steps, 3 iterations, assuming you can do all these additions in parallel. Okay? And if you start from 2 to the power p numbers, this algorithm will take p steps, p being the logarithm in base 2 of the number of entries. Okay, so this is the, I believe this is the maximal theoretical performance, in the sense that no algorithm can beat this for summing all the entries of the curve. Now, regarding CUDA, it's probably unlikely we will reach this level of parallelism, because you can only, how to say, the maximal number of operations that can be done simultaneously is 1024 threads that belong to the same block. And you cannot synchronize things across blocks, so probably you cannot have this algorithm implemented in CUDA with more than 1024 values. So what I will explain in the following slides is a kind of hybrid algorithm where you do in parallel the sums. So you assign one thread per entry of the array. You do in parallel partial sums inside each warp, so each group of 32 threads. And then you can also do in parallel the partial sums over each block. So that this time you will need shared memory for that. And then, so now you have one sum for each block. And then the sum of the values of obtained in each block, they will be calculated sequentially. But usually, it's a lesser problem than doing sequentially all the sum. So let me start with the reduction, so calculating the sum within a group of 32 threads, so within one warp. So for this, there is a function which is doing exactly this. So the function that will compute this sum is written here. You see it takes 4 lines, basically. You call it, so each thread in the warp is calling the same function with the value it was assigned at the beginning. So this here, this, and then the outcome will be also a floating point number. And then it has, so maybe I should explain the syntax here. Offset is a number that starts at 16, and at each iteration it's divided by 2. So the successive values of this offset are 16, 8, 4, 2, and 1. And when it reaches 1, this function stops. The loop, the for loop stops. And then this function, which has a name I cannot pronounce, is doing this. So the first argument here is a mask which tells the value FFFFF tells that just the 32 threads are participating in the operation, and that's usually the way. I've only used this function with this settings. So you call it with this value and the offset. So what it returns is, if it's called by the thread number I, it will fetch the value at I plus offset. So in the first iteration, it will fetch the value which is 16 addresses further, and it will add it to its own value. So this is what is done here. And what is illustrated in the figure here are the last 3 steps of this algorithm. So when the offset are 4, 2, and 1 respectively. So let's look first at the first line. So when you reach the step 3 steps from the end, you have 8 values in this array. And let's assume for the sake of the example that these values are all equal to 1. So when you call this function, you will take this value here. So the thread 0 will use its own value and the value which is at the offset 4 from itself, and it will add them up and store in its own entry of the array. The thread 1 will use its own entry and the one which is at the offset 4, so at the address 5, and store it in place of the value it had before, and so on. So the 4 threads will do that. So now you reach the second step, or 2 steps from the end, and you have now an array with 4 entries, and they all contain 2. And now you call the same function, but with the offset equal to 2. So the thread 0 will use its own value and the one which is located at the offset and add them up. And the thread 1 will do the same and obtain 4. And then the last step has offset 1, and the thread 0 is looking at offset 1 and adding the 2 values. And at the end of this function, the first thread in the group of 32 holds the value of all the elements that were present in this array of 32 values. And this was done in 5 steps, because if you look here, the offset starts at 16 and the function terminates when the offset reaches 1. So you have 5 steps, and at each step, all the additions are done in parallel. So instead of 31 additions, you need 5 steps to complete the sum of these 32 numbers. So now you have another function for doing the sum at the level of one block. So this is called by all the threads in the block. It has 2 arguments. One is the value that is held by a particular thread, and the other is an integer which is a thread index. So it's an integer that labels the thread within the block. So it's from 0 to the block size -1. So here, the first thing we do is that we declared shared memory. So it has to be of the same type as the numbers you want to add. So here they are floats. And you see it's a very small array of shared memory. It has only 32 entries. And in fact, you don't need more than that, because it's used for holding the partial sums corresponding to all the warps. So this 32 comes from the following. The thread has 1024, a block, thread, a block has 1024 threads at most. This is a limit of CUDA, so there cannot be more than 1024 threads in a block, and 1024 is 32 times 32, so this is the size of the warp, the number of threads in the warp. So it means that in a block there cannot be more than 32 warps. Okay? So if you want to store the partial sums for the warps in a block, you need at most 32 values. So this is why what goes into this 32 here, you will never need more than 32 numbers to store these partial sums. So now there is a little bit of juggling with the indices. The first one takes a reminder of the division by 32 of the thread index, and that gives you which is the thread index within a warp, so it's a number between 0 and 31. And the second line is taking the integer division of the thread index by 32, and that is a number that tells you which warp we're talking about. So the thread 0 is warp number 0, and it has a thread index 0 inside this warp. and the thread 35 is in the warp 1, and it has the thread index 4 within that warp. Yes. So now each thread calling this function will first call this function that does the reduction within the warp. So first do the sums within each warp, and if the thread index in this warp is 0, you store the value to shared memory. So each warp is storing in shared memory the partial sum of the corresponding warp. And you see here, so this is the part where you write to shared memory. And in the second part of this function, we will read back these values. But we need a sync threads between the two, because it's not the same threads who will do the reading than the threads who did the writing. So you need this synchronization barrier in between. And then you have 32 values in this array of shared memory corresponding to the partial sums within the warps. And you again want to sum these 32 numbers. And in fact, since 32 is also the size of a warp, you can call once more this function that does the sum inside the warp to find eventually the sum for all the numbers in the block. And the total number of steps required to sum all the numbers in the block is like calling twice this function that has a reduction in a warp. So it has 5 steps each. So in total, you will need 10 iterations. And of course, the 10 iterations come from this. You can have at most 1024 numbers, threads in the block, and within a block you reach maximal parallelism because you're using each time these parallel functions. So in fact you need only the logarithm of 1024 in base 2 steps. So this is 10 steps. Yes.
Let's say you have vector blocks.
So here, at least you will have to rethink a little bit the details. The logic will be the same, but you will have to rethink a little bit. So here, they are designed to work when you have one thread per entry of the array. So if you have an array with 1024 elements, you call this function with 1024 threads. Yes, no, but so yeah, in this operation, in fact, so you call that with 8 threads, but only these are active. So this one fetches the number here and adds them up. I don't know if it's really all the work is done by thread 0 or if they cooperate in some way, but you could think that say the work is done by thread 0, 2, 4, and 6, and 1, 3, 5, and 7 are doing nothing. So yes, that's the way it is. It's not a big problem in CUDA. So if you're used to OpenMP, where the creation of threads is something which has a significant overhead in CUDA, and also switching between threads, so going from thread 1 being active to thread 2 being active, also this switch as an overhead. In CUDA, the threads are much lighter entities than OpenMP, and you can switch threads very easily, and that costs very little. And also creating threads costs also. So here it seems you're creating half or twice too many threads. but the, how to say, the impact on the overall time it takes is so it simplifies the.
Where is the iteration being done in this piece of code? Is it in warp reduce sum or in sync thread?
The reduction is not
The iteration.
the iteration is done in warp reduce sum because it contains a loop. Let me show it again. So you see here there is a for loop, and this for loop will iterate over decreasing values of this offset from 16 to 1. So this loop is run 5 times. And then you're calling this function twice in sequence, so in total there will be 10 iterations.
Is the compiler intelligent enough to perform this operation automatically when you check the code? Like that?
No, this is something you have to put explicitly in your code.
Compiler is not cannot check if that perform a sum of
no, not in CUDA, not in C. There might be some languages which have built in these reduction operations, but I'm not familiar with it. So in C and CUDA/C, you will have to do explicitly. But you know it's a function that you don't even have to invent it yourself. I found it on the internet, of course, and you just copy it and paste it. Once you understand the logic, you can. I will show you that later. You can modify it to perform other operations. You just have to rewrite, modify them slightly.
In principle, just looking at the example, it doesn't matter which offset you use, right?
No, the offsets are powers of 2 because, in fact, it's not. So this was to explain what's the best algorithm you can achieve, but the tree is organized in a slightly different way. The way this function works is that you have your 8. So in fact, you start from 32, but I'm not going to draw 32 squares. And so the first operation, the first iteration will have offset equal 4, which means that this one will be combined with the one which is 4 cells further away, and then you do an addition and put it. But you put it back where you have it here. Then this one is taking the value which is at offset 4 as well from itself, and it writes the sum here. This one is combined with the cell which is at, so here it's offset equal 4 for all of them, and the last one is this one, which is combined with this one. And then the second iteration is doing the same thing, but using only these 4 values with offset equal to. So,
Okay.
So you start from 32 and the offset is 16, half of 32, and then the next stage is offset equal 8.
Until the last, which is offset 1.
Yeah. But this, in a sense, this function is doing that automatically, the address calculation. You don't have to code that yourself. And I don't really know how it works, whether it's, how to say, this function is, in a sense, is hard-coded in the hardware, or whether it's doing that in software. To some extent, you don't have to worry about that. It's transparent to you. So now, when we are at this stage, you have the block level sum in thread 0. it's an output of this function, block reduce sum. So thread 0 has a sum of all values that were in the block. And then you need an extra layer to sum these partial results across the blocks. So now it's another function that will do the sum for the entire grid of the entire array. So here, for the code to be simple, I assume that the size of the array is a multiple of the block size, so a multiple of 1024. If it's not, then you have to treat as a special case the last partial block. So you have this function which is it has it's a CUDA kernel. It has a first argument which is the array that you want to sum. A second argument is a pointer to where you want to put the sum, and this variable sum is located on the GPU. And it's called with one thread per entry of the array. So you first store in a temporary variable the corresponding value, A at this index. You compute the index from the block index and the size of a block and the thread index. You have to put this sync warp to make sure that all the threads in the warp have stored or have read from memory. Otherwise, you run the risk of calling this function too early while one thread in the warp, one or more threads in the warp have not yet read the array, the values stored in the array. So now you call this, each thread calls this function, and the outcome is the sum across the block. So the sum for this the group of 1024 threads. And then this is where you have to resort to this atomic add function. It's called only by the thread when the thread index is equal to 0. So by the first thread in the block, it's because when this function returns, the sum inside the block is present in the value which is returned to the thread 0. If you do that in another thread, I believe the result will be incorrect. And this line is essentially summing in a safe way the partial results obtained in each block, and because atomic add is excluding, it can be executed only one at a time. This part is serial, but it's less of a problem because suppose you start from 1 million entries in the array. You first divide this array in 1024 blocks of size 1024. And within each block, the sum is calculated by exploiting in full the possibilities of parallelism. And you only have 1024 sums at the end that will be done sequentially, but you've reduced, you see, in the naive algorithm I showed before, the bottleneck was doing all the sums sequentially, 1 million sums sequentially. While here it's only 1,000, and it's still a bottleneck, but since there are only 1,000 of them to be performed, it's not a big, this has not a big impact on the performance. So the way this CUDA kernel is called is that you first need, it's your responsibility to initialize this, variable on the GPU to 0 before you start summing into it, because you see in the CUDA kernel here there is no place where it's set to 0. So you have to call it after having set this sum to 0. So it's done with this first line, and then you call this kernel with size being the number of entries in the array, So the first argument is the number of blocks, so you divide it by 1024, and you have blocks of size 1024 when you call it. And the outcome is that now, when the kernel finishes, the variable sum is having the sum, is containing the sum of all elements, and you still need one more call to retrieve it on the host if you want it. So the number of steps overall of this algorithm is the number of blocks times 10. So because for doing the full sum within a block, you just need 10 iterations. So this is the number of blocks times 10. And the naive algorithm takes a number of iterations, which is the size minus 1. So you see you gain roughly a factor of 100 in the number of iterations. And I coded that on my laptop to compare these various possibilities. So I took arrays of, I believe this is 500 million floats, so 2 gigabytes, and I repeated 256 times. This is just so that the measurement of the time is more accurate. It's not, yes.
Back all the value you computed in all the different blocks and give it back to the first one to do it again. Then it makes sense.
Yes, it might make sense. I've never seen this implemented in the examples of code you find on the internet. So perhaps it's definitely possible, and I'm not sure there will be a big gain, if at all, by doing this. And perhaps if this is by far the most common way of, or the most common implementation one finds for this, and probably some more competent people than me have thought about this. Perhaps this is near optimal. So I have 3 versions of this reduction. One which is running on the host, so on my laptop that has 6 cores with OpenMP. One with the naive CUDA version, which I already showed you, performs very poorly, and one which is implemented according to this 3-layer strategy I explained now. And you see, so on the host, it takes 32 seconds. The naive version on the GPU, which is fully serialized, in fact, takes almost 5 minutes. And on the GPU, using this layered algorithm, takes 8 seconds, so 4 times faster than on the host. And for some reason, in fact, this algorithm on the GPU produces a result which is much closer than the sum computed on the host, and I have no feeling why it's that. When you do a reduction in OpenMP, you also don't control how the partial sums will be done. It depends on how the threads are, how the iterations of the loop are assigned to every thread. And it's something which usually you don't control. You can, but by default you don't.
What is the result?
Which one is the most accurate? That's the question. I'm not sure, in fact, because the correct way to assess that will probably be to start with the same array of numbers, promote them to double precision, compute the sum in double precision, and hope that it's more accurate than the sum done in single precision. So that will be your reference. And then you will have to compare these 3 values to the sum computed in double precision to see which one is the closest. I don't know, I didn't try. But you see, in single precision, you have roughly 7 digits of accuracy at every operation. But here you're doing 500 million additions. So suppose you, and these errors accumulate. They don't accumulate always in the same, they don't drift always in the same direction. So it's better than having an error that accumulates only in one direction. Sometimes the error is positive, sometimes the error is negative. So overall, the final error is less than 500 million times the error for one operation. But it's not too surprising that the sums start differing after either the fifth or the fourth digit, given the accuracy of each operation and the number of operations you do. It's a basic and a sad fact of life with single precision, I'm afraid.
Actually, low precision would make these times.
Oh, so yeah, the thing is that with double precision, it will have almost no impact on the reduction done on the host, but it will have a significant impact on the reduction done on the GPU, at least for the GPU of my laptop, because it's much slower in double precision. If you have a professional grade GPU, one of the very expensive ones, that can perform computations in double precision almost as fast as in single precision, perhaps it would. No, in fact, I have to withdraw what I said, because it could very well be that this algorithm of computing the reduction of a reduction is memory bound and not really. It's a tricky thing to assess, because even if it's memory bound, if you work with floats, you will have to transfer twice as more data. If it's just memory bound, you would expect this time to double, for instance, because you just have to read twice more data, in volume of data in memory, than you would with single precision. If it's compute bound, because on my laptop, the the peak performance, so the number of operations per second is, I think, 32 times less in double precision than in single precision, then the time will really explode. If it's memory bound, there will be a slowdown, but less. The reduction on the host could have the same issue. I don't really know if this 32 seconds is limited by the performance or the bandwidth with which we can read from memory, or whether it's more limited by the number of additions we can perform per second. Not very sure.
Just to have a feel, so this 2 to the 29, is it a big number, or is it a small, let's say for...
It's a rather biggish number for my laptop, because my laptop has a GPU that has 4 gigabytes of memory. I tried with twice more, so 2 to the 30, and that will use 4 gigabytes of memory, but because there is a little bit of extra bits I need, it didn't fit in the memory of my GPU. So in fact, 2 to the 29 is the largest power of 2 I can fit in the GPU of my laptop. For more serious GPU, you could have much larger arrays. There are GPUs with 64 gigabytes of memory, but you will not. You could increase by perhaps a factor of 40. You will not have an array with 1,000 more entries, even on a super expensive GPU. Now, of course, if there is always a possibility of doing the sum chunks by chunks. So if your array is too large to fit on the GPU, you divide it in 4 chunks, for instance, and you do partial sums on this sub-arrays. Yes, there is a remark here about accuracy. So I'm comparing these two, not the one with the naive reduction, for which I don't know how the error comes about. The relative difference between these numbers is about 2 10 to the minus 5, but this is after 500 million operations. So I think it's pretty good. In fact, it's after 500 million operations in single precision, I will even, this is not too surprising, given that the relative accuracy of one of these operations is about 10 to the minus 6. Okay, so now one thing I want to explain in the last 5 minutes is how you will modify these functions if you wanted to do a reduction that involves some other operation. So not an addition, but something else. So here I've taken the example of the calculating the logical end of a lot of conditions. So the result of a condition in C is of type int. In fact, it's more precisely an unsigned int, so a positive integer. So first of all, the quantities we're going to manipulate are not floats, but of type unsigned. Okay, so everywhere we have float, we have to change to unsigned. The logic is pretty much the same. The only thing that changes is that, of course, the return value is also unsigned. And here we had a plus, and now we put the logical end. Okay, that's all. That's the only change in this function. And of course, you want to change its name because you cannot have two functions with the same name. And then for the reduction at block level, it's also the same. Everywhere there was a float, you put unsigned. And then you, instead of calling this function for doing the sum, the warp reduce sum, you call warp reduce end. And then the other change is, it's here, of course, in this call. And here there is another difference. If you remember, or perhaps you don't, the value here was 0. The 0 here is not by accident. It's a neutral element for the addition. So it's what you should use if you have less values in your array than the size of a block. So you replace the missing ones by 0. And when you want to do that for the logical end, you have to use a neutral element for end, which is any positive number. 1, any positive integer. So here I've put 1, and that's the only difference. And then for the final layer where you do the reduction across the blocks, you need another kernel. You change the type of from float to unsigned for both the array and the values, the variables that will hold the result of the reduction. Instead, here you had float before it becomes unsigned. You change the function you call here, and instead of doing atomic add, there is a CUDA has a function called atomic end, which does the same thing but for the logical end operation. And of course, you initialize the initial value of these variables that will hold the final reduction should be the neutral element for the end operation. So you don't initialize it to 0, but you initialize it to 1. Okay, that's all. And this way you could compute if you have a certain test that you want to check, for instance, that all the values in an array satisfy a certain condition. You will have as many threads as you have entries in the array, and then each thread will compute this condition for the corresponding entry, and then these functions will compute the logical end of these conditions to tell you if all the elements in the array fulfill the condition. So I will stop here for today. And I just want to advertise what I'm going to talk about next week. So next week, the goal is twofold. A big part of next week will be devoted to discussing some aspects of how one achieves good performance with CUDA. So a big part of that, at least for algorithms that read a lot from memory, is to tune the way you access the memory in order to have good bandwidth. And I will show an example which illustrates the possibilities for that. And the second question is how many threads should you use? Is it better to have a small number of threads or a comparably super large number of threads? And then the final part, in the final part, I want to discuss some libraries which are provided by NVIDIA using CUDA that perform some of the most frequent tasks in either numerical analysis or in other problems. So if, how to say, if you need something to perform a task which corresponds to what is done in one of these libraries, I would recommend spending time to learn how to use it rather than writing it yourself, because these libraries have been written by by software engineers working for NVIDIA, and they are super familiar with hardware, with programming. Probably, most likely, there is no way you can write something that performs better than what they obtain. And the second bonus, of course, is these libraries exist, been around for a long time now, some for more than 10 years, and all the most visible bugs have been fixed. So okay, so let me stop here for today.